Hello friends, welcome to this next video on fixed point iteration method. In the last video what we have done, we have derived the theory for fixed point iteration method. So we have derived basically one theorem, and in the theorem everything which is required for the fixed point iteration method was described. So that theorem we will try to apply on some of the numerical problems. So I'll give you one question. So I'll start with this question that you have to show that a function g of x which is defined by x square minus 1 by 3 has a unique fixed point in the interval minus 1 to 1. What can, and there is a further part to it, what can you say about the interval 3 to 4? Okay, so first of all let us just go into basics and just apply the fixed point definition on this function. You have x square minus 1 by 3 and you are looking for a point, you are looking for p, this is your g of x. You are looking for a fixed point means you are looking for a p such that p is equal to gp. So basically you want to find out where this graph cuts the graph of y is equal to x line. So can you draw the graph for this particular function? This is y is equal to x square minus 1 by 3. So this is your parabola. This is your parabola. And you can draw this parabola. The parabola goes like this. It cuts the axis at plus minus 1. So you have minus 1 here, plus 1 here, and it is an upward parabola like this. Okay, so this is the parabola and this is the line y is equal to x. So this is your x square minus 1 by 3. Y is equal to x square minus 1 by 3. Okay, fine. So you can see these are the 2 points of intersection, this point and this point, and we can clearly see this particular point because this is 1. This particular point, it lies in the interval minus 1 to 1, and so it means that minus 1 to 1 there is a fixed point. And next they are asking about 3 comma 4. So we don't know what point is this. You can just basically we are looking for x square minus 1 by 3 is equal to x. So you have x square minus 3x minus 1 equal to 0. So you have x is equal to minus 3 plus minus root 13 by 2. So there are two roots. One of the root is minus 0.3027 and another one is 3.3027. So these are the two roots of the equation. It means that these two are the fixed points. So can you see this first fixed point is in the interval minus 1 to 1 and the another fixed point is in the interval 3 to 4. So it means that in both the intervals which they are asking for, there is one fixed point. Now let us try to apply our theorem. Okay, so in the interval minus 1 to 1, what is your theorem? Theorem says if the three conditions are satisfied. What are the three conditions? First is g should be continuous. So here your g of x is x square minus 1 by 3. Being a polynomial function, this is continuous everywhere and in particular in the interval minus 1 to 1. Now let us see, second condition is g of x should be in the interval minus 1 to 1 for all x in minus 1 to 1. So let us check whether this condition is true or not. So for that it is very simple. When x is in 1 to minus 1, what is your x square? X square is going to be in between 1 and 0. So your x square minus 1 is going to be between 0 and minus 1. So you have x square minus 1 by 3 is going to be between 0 and minus 1 by 3. So can you see your domain is minus 1 to 1 and your codomain is minus 1 by 3 to 0. It means that this is the range for g of x, this is the range for x. So you are inside the range for x. So this is what was required. So you can write it as g of x is between 1 to minus 1. There is no problem if you are inside this, because this is 0 is less than 1 and minus 1 by 3 is also greater than minus 1. So you should be inside the original domain. So second condition is also true, and third condition is g dash x should be strictly less than 1 for all x in minus 1 to 1. So let us see whether this is true or not. What is your g dash x? G dash x is 2x by 3, and you want to see what is the modulus. You can see that for these values of x, this is strictly less than 2 by 3 into 1. So this is strictly less than 1. So all the three conditions are true in the interval minus 1 to 1. Therefore, the fixed point theorem, which we have done in the last video, the fixed point theorem tells us that there is a unique fixed point in the interval minus 1 to 1, which we have seen otherwise also. Here also we have seen by drawing the graph and by solving this equation, we had seen that there is this unique fixed point in the interval minus 1 to 1. Now let us try to apply the theorem in the interval 3 to 4. So if you apply your theorem in the interval 3 to 4, in 3 to 4, you see what is g of 4. G of 4 is 4 square minus 1 by 3. This is 15 by 3 is equal to 5. So your g of x does not lie in the original domain. So second condition is violated. First is of course true, continuity is true. Second is violated. In fact, third is also violated. You can check what is the derivative at g, derivative of g at 4. It is 2 into 4 by 3, which is greater than 1. So fixed point theorem is not applicable here. Still, we have already seen there is a unique fixed point. There is a unique fixed point in the interval minus 1 to 1. So the motive is, so from this question you understand that fixed point theorem is a one-way path. One way. It means that if all three conditions are true, all three conditions are true, it implies a unique fixed point. But if some of the conditions are not true, you cannot say anything. There may or may not be the unique fixed point. If some of the conditions are not true, you cannot say anything. Can't claim anything about the fixed point in that interval. True in some interval. Of course, we are talking about an interval. You can't claim anything about the fixed point. So you don't have to say no when you see that conditions are not satisfied. Okay. So this was first problem. Now let us see another problem. So you have this problem that you have to find out an interval for g of x is equal to 5 by x square plus 2 in which unique fixed point exists. So in this particular problem, you are not given the interval, you are asked to find out the interval in which the unique fixed point exists. So basically you are looking for an interval. So how the solution goes, you are looking for AB, looking for an interval AB in which g of x is continuous, g of x belongs to AB for all x in AB, and third is g dash x should be strictly less than 1. Okay, so this is what we are going to do, but to start with we must have some guess about where the fixed point could be. So for that we have 5 by x square plus 2 is equal to x. If I try to solve it, I'll get a cubic equation and I am not able to solve that equation. So what I can do, I can just guess where this equation has a solution using intermediate value theorem. So you have this x cube minus 2x square minus 5 is equal to 0. So this is your equation, and you can just check f of 0 is negative, f of 1 is negative, f of 2 is negative, f of 3 you can check, this is 27 minus 18 minus 5, this is 4 positive. So at 2 it is negative, 3 it is positive, and this function is a continuous function. So intermediate value theorem tells me that in the interval 2 to 3 there is a root of this particular equation. It means that there is a fixed point for this particular function, because root of this equation is a fixed point for this particular function. Okay, so I'll start with the interval 2 3. So I start with the intervals 2 3. Okay, now I will check the conditions. First condition, continue, g of x is 5 by x square plus 2. So you check g of x is continuous, no problem. Then go for the second condition. Second condition is your g of x should be in 2 3 for all x in 2 3. So you start with x in 3 2, and you want to see what is the range for this function. Just go like this, x square is in 3 square to 2 square, and then your 1 by x square is between 1 by 2 square and 1 by 3 square. Okay, fine. And then you have 5 by x square is between 5 by 2 square and 5 by 3 square, and just add 2. Right, so you see that this particular value, this exceeds, this is actually 2 plus 5 by 4, so this is 2 plus 1.25, so 3.25. so you are at, and this is the value of g at 2, right? So it means that you are exceeding, your initial interval was 2 to 3 and you are going outside 3, you have 3.25 here, so you don't want that, right? So I want to reduce this quantity, and for that what can I do? Because I have a control on this interval, this is my choice, so I can change this 2. If I increase this 2, then because this 2 is in the denominator, this quantity on the right hand side will decrease. So what I will do, I will go back to my analysis. Here I had checked f of 2 and f of 3. If I check f of 2.5, you can check it, that is also negative. It means that I can claim there is a root between 2.5 to 3. Here I had claimed that there is a root between 2 to 3 and the fixed point is also in the interval. And now I have narrowed down my interval to 2.5 to 3. So now if you start with the interval 2.5 to 3, right? So your first condition, continuity, is okay. Second condition, let us see, x is between 3 and 2.5. Then like above, your x square is between 9 and 2.5, this will be, yeah, correct, 2.5 square. So 1 by x square is between 1 by 2.5 square and 1 by 9, and you multiply with 5 and then you add 2. So this is what you will get, and if you do the calculations, you will get it to be 2.56 less than g of x less than 2.8. So you see, you start with the interval 2.5 to 3 and your g of x is also between 2.5 to 3. So basically this should happen. This is the range for x, and you see what you are getting 2.56 to 2.8. So this is the range for g of x. So that condition requires that range for g of x should be inside the range of x. So second condition okay, first condition okay. Now let us see the third condition. Third condition is g dash x. What is g dash x? This is 10 upon x cube, because you have 5 by x square plus 2 g of x. So you are minus 10 upon x square, x cube. What is the maximum value of this in the interval 2.5 to 3? Because this is a decreasing function, because we are considering the modulus. So the maximum value is at the point 2.5. So you have this is less than is equal to 10 upon 2.5 cube. So it means that, and this is, if you compute, this is 0.64, which is strictly less than 1. So all the three conditions are satisfied in the interval 2.5 to 3. So 2.5 to 3 we can claim for from the fixed point theorem that there is a unique fixed point for g of x is equal to 5 by x square plus 2. So these are the problems which are for the fixed point iteration method. There are so many more problems we'll do later on.